Section 2.4, the precise definition of a limit. Let f be a function defined in some open interval that contains the number a, except possibly at a itself. Then we write that the limit of f of x as x approaches a equals L if for every number epsilon greater than 0, there is a number delta greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. So this is a fancy way of saying that if the distance between x and a, that's this, is less than delta, then the distance between f of x and our limit is less than epsilon. So we're basically saying that for any possible distance that you would want the limit to be close to the function, it is possible to force the limit to be within that distance by taking x to be within some distance of the number we're approaching. So let's use a graph to find a number delta such that if x is within delta of 1, then f of x equals x cubed minus 5x plus 6 is within 0.2 of 2. So our entire point here is that this is one potential epsilon. In this case, we want to try to force the function to be within a distance of 0.2 of our potential limit of 2. For our definition to work for the limit, for it to actually be equal to 2, it would have to work for every possible epsilon, not just this 0.2. But we're going to warm up a little bit before we do another example that works for every possible epsilon. So we want the absolute value of x cubed minus 5x plus 6 minus 2. And remember, absolute value represents distance. So this means the distance between this function f of x and 2, we want to be less than 0.2. We want it to be very close. But how close? Within 0.2 close. Absolute value is the same thing as a triple inequality when it's less than. So this will be negative 0.2 less than x cubed minus 5x plus 6 minus 2 less than 0.2, and we can just add 2 to every side. So 2 minus 0.2 becomes 1.8. We still have our x cubed minus 5x plus 6, and we have now 2.2. Okay, let's pull out our handy dandy calculator emulator. Go to y equals. We will put in x cubed minus 5x plus 6. We want to restrict it by 1.8 and 2.2. So we put those in for y2 and y3. Take a look at a graph. Okay, we could see our restricting lines are a little bit too small, so let's try getting a little bit closer and zooming in. I want to zoom in right around where they look like they're intersecting. Okay, we want to be around the point 1, 2 because we're trying to get within delta of 1 for the x value. So we want to be very close to 1. Alright, that looks pretty good. You can see that x is 1.02 whatever, so we're pretty close to 1. And on the left, we've got the y value 1.98 whatever, so we're very close to 2. So let's find these intersection points. Second trace to get to the calc menu. Intersect number 5. Our first curve will be this one, yes. For our second one, let's get that one. And we want to guess over here. So our intersection is, looks like about 0.91 for the x value. Let's get the other point of intersection now. And we can use that for the first curve. go, that's our second curve. And we're guessing it's over there. Alright, intersection looks to be at about 1.12. Okay, so this means, let's put our calculator back, that if x is between 0.91 and 1.12, then that'll force our function to be within 1.8 and 2.2. Which should make sense looking back at our calculator. If you plug in 0.91, then you get a little bit more than 2.2. We should probably actually be a little bit careful here. Let's make this a little bit bigger. Oops, come on. 0.92, let's go. Because that way, when we're looking at our function, we're going to force it to be even smaller than 2.2. If we go a little bit bigger in the x value, it goes a little bit farther. And I think we should still be good with the 1.12 because it was even more than that. We cut it off. Okay, so let's try to make this thing symmetric around 1. So we'll try to subtract 1 from all three sides. We get minus 0.08 is less than x minus 1 is less than, let's see, 0.12. So it looks like we could just have x minus 1 being less than 0.08 when we take the absolute value. I'm choosing 0.08 here instead of the 0.12 because I can just make it as small as I want. I can choose any delta I want, given the epsilon. The epsilon is the thing I don't have any control over. But my reaction to epsilon is choosing some delta, so I can just choose it to be smaller than 0.08, and then I cover both bases. If I chose it as a 0.11, then that would be maybe a little bit too big for that 0.08, so I'm being conservative here. Let's choose delta equals 0.08. Okay, then according to our calculator, if the distance between x and 1 is smaller than 0.08, then our function will be restricted, or the distance between our function and 2 will be within 0.2. And this makes sense from our graph. Remember, if x minus 1 is less than 0.08, that's saying the distance between 1 and the x value is less than 0.08. That means I'm going from this point to down here to this point for x. That's what my first condition means. So if I'm between those two x values, of course it's going to force us to between the two y values here. This y value of 1.8 and this top y value of 2.2, which is exactly what I wanted to force us to be in between in order to be within 0.2 of the limit 2. Let's prove that the limit of 4x minus 5 as x approaches 3 is equal to 7. In this case, it's kind of like a game where if I give you any epsilon value, it could be the 0.2 from last time, or it could be even smaller, 0.0002, however small I decide to give you the epsilon value, you have to be able to respond to me with a corresponding delta value that'll force my function to be within that epsilon value distance of the limit, in this case 7. If you can't always give me a delta, then the limit doesn't exist. In this case, we're saying to prove it, so we're assuming that the limit is going to exist, but we want to show, I'm going to write WTS for want to show, that if our distance between x and 3 is smaller than delta, then that will force the distance between our function and our limit to be less than epsilon. And it should make sense. If this limit actually is 7, then I should be able to get as close to 7 as I would like for my y value. If I can't get within any epsilon distance close, then it must then actually be the limit. Okay, so we have to find some sort of delta that will always work. So that means that the delta is going to depend on whatever the epsilon is that we're given. So it's going to be some sort of function of epsilon. In order to figure out a delta that can correspond to the epsilon, we need to sort of manipulate our two conditions so that they kind of match up to each other. So I want to somehow manipulate my epsilon condition to get an x minus 3 in there. That way it'll match up with the delta condition, and it'll kind of suggest to me what my choice of delta should be. So let's write 4x minus 12, just to simplify things. And then we can take out the 4 by factoring it. Absolute value of a product is the product of the absolute value, so I could take out the 4 from the absolute value. And then I can divide by 4, because it's not 0. Okay, now I've got an x minus 3 in both of our conditions. I know that if x minus 3 is less than delta, I want that x minus 3 should be less than epsilon over 4. That's the exact same thing as my original condition. So if I already have it being less than delta, and I'm allowed to make delta whatever I want when I respond to epsilon, I can get as close to 3 as I would like, is what I'm saying, then if I can choose anything, I might as well just choose delta equal epsilon over 4. So let's do that. Okay, now that we've chosen delta equals epsilon over 4, it should make intuitive sense that this is going to work out based on, what we did in order to suggest our choice of delta. However, part of a proof is to actually verify that the choice you made works. So we have to actually write if x minus 3 is less than delta. Now we have to show that 4x minus 5 minus 7 will be less than epsilon. But this is the easy part, because we're pretty much redoing the work we already did. We simplify it to 4x minus 12. We pull out the 4. We know that this will be less than 4 times delta, because we just said that x minus 3 is less than delta, absolute value. However, we also said that delta was equal to epsilon over 4, so I can substitute that in for delta. The 4's cancel, give us 1, so we have 1 epsilon, exactly as we wanted. So there we go, we proved it. That implies the limit as x goes to 3 of 4x minus 5 does equal 7. I'm basically saying, if you were to tell me that you want it to be within 12 units of the limit, then I would say, okay, take 12 divided by 4, you get 3. Then I want x to be within 3 units of 3, and that'll force the function to be that close that you wanted to that limit. And you might say, oh, okay, well, I'm going to choose another epsilon. I'm like, okay, well, whatever, it doesn't matter. I could choose another delta because I'll just divide by 4 every single time. I can even see what this looks like in a graph. So let's say here's 4x minus 5. here's 7. We're going above some epsilon value. So here's 7 plus epsilon, and below some epsilon value. We want to find some sort of delta value that will work. So we know that 3 corresponds to 7. F of 3 equals 7. If I go, let's say I want to force these two conditions to hold. So it should make sense that I can do that by going to the left some delta and going to the right some delta. And you can see that the delta interval is smaller than the epsilon interval, which makes sense. I'm dividing by 4. If the limit didn't exist, it could look something like this, where instead of just going up all the way, maybe I stop over here and then I jump up. Intuitively, it makes sense that this limit does not exist, because as I go from the left and I go from the right, I approach this value from the left and I approach this value from the right, and they don't match. Let's say I was to guess that this value is the limit. So then I would go a little more. Plus epsilon, minus epsilon. If this thing is the limit, I should be able to restrict delta to be able to get some sort of restriction here around my x value. So I have to include the x value I'm approaching. So we'll call this x value a, because this is a more general example. Do a better job with that. I have to go to the left of a little bit. Okay, so then this would be a plus delta, a minus delta. Notice that no matter how you restrict delta in this case, this is going to end up cutting off around the function at the top and bottom, and I'm going to miss this entire part over here. So I'm not going to be able to force my function to be arbitrarily close to the limit no matter what delta I pick, because I have to go some distance away from a, and any small distance will always leave a little bit of this graph over here left, and I don't want any of that. Well, I mean, I do want all of that to be inside of this box, but I can't force that no matter what delta I choose. Similarly, if we thought that the limit was over here, we could draw the lines over here, and then over here this would escape. We don't have that problem over here, because there will always be a bit of the function around. No matter how small I make my epsilon interval, there will always be a function nearby, a part of the function nearby. Okay, let's talk about right and left-hand limits. For a formal definition, the limit of f of x equals L as x approaches a from the left if for every number epsilon greater than 0, there is a number delta greater than 0, such that if a minus delta is less than x is less than a, then the limit is close to f of x with an epsilon. So we're saying that we want x to be smaller than that number, which makes sense, we're on the left, and we want it to be within delta distance below that number. And on the right, it's the same thing, we want it to be within delta distance above the number. That's for the limit of f of x as x approaches a from the right. Let's do an example. Let's prove that the limit of the square root of x as x approaches 0 from the right is 0. So again, let's write out what we want to show. We want to show that if, in this case, we're doing it from the right, so we want to show that 0 is what we're approaching. That's smaller than x. That's smaller than 0 plus delta. Okay, if that's true, then we want that the distance between the square root of x and 0 should be smaller than epsilon. Well, this is the same as just square root of x when we simplify. So we can square both sides. Okay, so we wanted x to be less than 0 plus delta, which is delta. So if x is less than delta, we want that to force x to be less than epsilon squared. It makes sense to choose delta to be equal to epsilon squared. Remember, delta will always be a function of epsilon. And let's test it. So if 0 is less than x is less than 0 plus delta, which is delta, then the square root of x minus 0, let's look at that. Let's make sure that this thing actually is smaller than epsilon. Well, this is just square root of x, because the absolute value of the square root is obviously just the square root. And x is less than delta, so this is less than the square root of delta. But delta, we said, was equal to epsilon squared, so this is square root of epsilon squared, which is epsilon. All right, perfect. So that implies that the limit actually is equal to 0. So again, for every single one of these problems, there's two parts. Step 1 is we want to find a candidate for delta. So we manipulate one of the arguments, the epsilon argument or the delta argument, try to make them match up with each other. Then step 2, test the choice of delta, make sure it actually works, and it forces the function to be within epsilon of the limit. Okay, let's prove that the limit of x squared as x approaches 3 is 9. So again, we want to show that if 0 is less than absolute value of x minus 3 is less than delta, so slightly different than the previous example because this is a two-sided limit, then x squared minus 9, the difference between x squared and our limit, will be less than epsilon. Okay, so we want to try to make the epsilon argument and the delta argument match. So let's factor this. X plus 3, x minus 3. So that's what we want to show. So we just want x minus 3, then it matches. So we need that to be less than epsilon over x plus 3. Okay, so we have to be a little bit careful here. We need to make sure that we're not going anywhere that x plus 3 is going to end up being 0, which we aren't because notice we are approaching positive 3, so we're not going to be nearby negative 3 anyway, so we don't have to really worry about that. The other issue is that we want delta to be a function of epsilon. We don't want delta to be a function of x and epsilon. So we need to somehow find some sort of bound on absolute value of x plus 3. That way we could swap it out with some sort of constant and then just take absolute value of x minus 3 less than epsilon divided by some constant. So we want to get rid of the x plus 3. So let's start with what we know. We're going to make x minus 3 less than delta. We want that to force the other thing to be less than epsilon. So that means we want absolute value of x minus 3 less than delta to also force this to be some sort of constant, or less than some sort of constant. So, okay, what if we chose delta to be, let's say, equal to 1? Oops. Okay, so then that would make this true. which means that we can add 6 to all three sides so that we can get x plus 3 in the middle. Okay, and that means that the absolute value would have to also be less than 7. I'm choosing to disregard the 5 because if it's less than 5, it might be a little bit too restrictive, but less than 7 is on the safe side. I already know that x plus 3 is definitely less than 7. So I just needed some sort of number that would be smaller than, it doesn't really matter what, so I might as well just choose a 7. The issue is that in order for this thing to be less than 7, I had to choose delta to be equal to 1. So I know I'm going to want this thing to be replaced with a 7. So that means I'm going to want absolute value of x minus 3 to be less than epsilon over 7, which means that I should probably choose delta to be equal to epsilon over 7. So the issue here is that I need to reconcile that I need both of those criteria to be true. I need the thing to be smaller than 1 for it to be, I need x minus 3 to be smaller than 1 in order to make it smaller than epsilon over 7. So in order to make both of those things true, I need to just choose delta to be the smaller value. I basically want to make two choices of delta at the same time, so we use this like hacky little trick. Take delta to be equal to the minimum of 1 and epsilon over 7. That way, when it's smaller than 1, it'll force x plus 3 to be smaller than 7, which will force x minus 3 to be smaller than epsilon over 7. Let's watch that in action. So this is step 2 where we test it. So if absolute value of x minus 3 is less than delta, then we have absolute value of x minus 3. Well, it's less than delta. Delta is the minimum of 1 and epsilon over 7. So it's definitely still less than 1, which, as we saw before, indicates that x plus 3 will be less than 7. So that's good. And so we have absolute value of x squared minus 9. This is what we wanted to show is less than epsilon. We've seen that we can factor this. And we also know that x plus 3 is less than 7. We know that x minus 3 is less than 1 and epsilon over 7. So let's make it less than epsilon over 7 this time, because it's the minimum. And that equals epsilon. Exactly as we wanted. So that implies that the limit as x approaches 3 of x squared is equal to 9. Okay, let f be a function defined at some open interval that contains the number a, except possibly at a itself. Then the limit of f of x as x approaches a equals infinity means that for every positive number m, there is a positive number delta, such that if x minus a is less than delta, then f of x is greater than m. So we're saying that no matter what number you could pick the biggest number you could possibly think of, our function will still be bigger than that number. So that makes sense, you know, when we think about a limit going towards infinity, it's bigger than every number. And similarly, if we talk about the limit of f of x as x approaches a being minus infinity, that means for every negative number n, there is a positive number delta such that if x minus a is less than delta, then f of x is less than n. So no matter how small of a number you pick, or no matter how large negative of a number you pick, my function will always be smaller than it. Okay, so let's prove that the limit of 1 over x squared as x approaches 0 is infinity. We want to show that if x minus 0 is less than delta, so we're getting close to 0, then 1 over x squared needs to be bigger than every number m. Well, that's the same thing as saying that, remember, we're trying to make these things match, so I just want to get an x in the end, or absolute value of x rather. So let's flip these. I'm flipping the left and right sides, which means I flip my inequality. And I can take the square root of both sides. Square root of x squared is just absolute value, exactly what we wanted. Square root of 1 is 1, and then square root of m is whatever square root of m is. Depends on the number m. Okay, so now that our arguments match, it makes sense that we want to choose delta to be 1 over square root of m. So step 1 is done. We found a choice of delta. Step 2 is let's test that choice of delta and make sure that it works. So if absolute value of x, because that's what x minus 0 is less than delta, let's look at 1 over x squared. We want that to be bigger than m, but 1 over x squared is the same as 1 over absolute value of x squared, which we know is bigger than 1 over delta squared. And we chose delta to be equal to 1 over square root of m, so this is 1 over square root of m squared. And that means that the square root gets canceled by the square. 1 over m is just m. So 1 over x squared will always be bigger than m, as long as we choose delta to be 1 over square root of m. So the limit as x approaches 0 of 1 over x squared equals infinity, which, remember, is a fancy way of saying that it doesn't exist, but it gets arbitrarily large.